Hello, this talk will be about CPM categories for Galois extensions. Let's jump straight in and have a look at some of the motivations for this work. In quantum theory, we have decoherence maps, which allow us to study the transition between quantum theory itself and classical theory. These maps have many interesting properties, two of which will be of particular relevance for the remainder of this talk. Firstly, decoherence acts to send density matrices to classical probability distributions, which we can think of as vector quantities. And in doing so, it reduces the degrees of freedom of systems. Secondly, it acts to reduce the fields over which systems can live, sending the complex numbers to the positive reals. And it does this by picking out the diagonal elements of a density matrix. So we asked ourselves the question, can we try and generalize this? Could we perhaps construct some quantum-like theory, some classical theory, and do this in such a way that we have this tower of intermediate theories, ST. And in particular, we want this tower to have decoherence maps that allow us to move through the tower. And we want these decoherence maps to act in an analogous way to those of quantum theory. So firstly, we'd like them to reduce the degrees of freedom of systems, but also to reduce the degree of fields viewed as an extension of some base field. So we could imagine that these theories live over a tower of fields. So this quantum-like theory lives over the field big K. The classical theory lives over this field little k. And then we have all these intermediate fields F that each of these sub-theories live over. And as we decohere through the tower, we want to kind of move through this tower of fields. Okay, so let's start by recapping decoherence and the CPM construction, the usual CPM construction. So the CPM construction gives us a way of building a category of density matrices and completely positive maps from our category of pure maps. And there are two steps to this construction. We start with taking our morphisms F and folding them. So we pair F with its conjugate F star. And then we discard environment systems via the cap. If we start with a dagger compact category C, then we can build a new category CPM of C, and that has maps of the form on the right here, drawn with these darker lines. And it's worth pointing out that this new category is also a dagger compact category. Now, within CPM, there are certain maps that we call the decoherence maps, and these are given by these special commutative dagger-Frobenius algebras, also known as spiders. And these maps, if you look at what they do to a density matrix, they just zero out the off-diagonal elements, and they just return these diagonal ones. So they send this density matrix to a classical probability distribution. And we can capture this transition in a more categorical way by working within the Karoubi envelope of the CPM category. So the Karoubi envelope of our category, if we start with the category C, it's Karoubi envelope split of C. It's the category with objects that are an object A from our original category paired with an idempotent E on that object. And then the arrows of the Karoubi envelope F is an arrow from A to B, which is invariant under the idempotence. Now, by taking suitable subcategories of the Karoubi envelope of CPM, we can recover both the quantum and classical theories. So in particular, the full subcategory of the Karoubi envelope of CPM, spanned by identity maps, is precisely CPM itself. So we recover all the quantum systems. And the full subcategory spanned by decoherence maps, there's an equivalence of categories between that and the positive real-valued matrices, i.e. the classical systems. Now, the theories that we studied in this work arise by a generalization of this CPM construction. We start with an action by strict monoidal autofunctors of a finite group G on our symmetric monoidal category C. So by this, I just mean a homomorphism from some finite group G. into the monoidal automorphisms of C. We can then generalize the two steps of the CPM construction. Firstly, by folding according to the action. So that means we tensor over the image of F under each one of the autofunctors phi of G for each element of the group. And then we discard by some suitably chosen effects. Now let's see how this works in more detail. So firstly, the folding. We can define, given our action, an endofunctor on C known as the folding functor. And all this does is sends both objects and morphisms to their tensor product over their images under the action. Then the image of this folding functor gives a new category, fold of C. And this category has many nice properties, but in particular, it's essentially invariant under the action of the group G. So stated formally, this just says that the autofunctors phi of G restrict to functors on the folded category. And here they're naturally isomorphic to the identity on that folded category. And this essentially occurs because any phi of G acts on this object just to permute the elements of this, sort of the factors of this tensor product. And we can recover the original ordering just by braiding everything. So by the symmetry isomorphisms coming from the underlying symmetric monoidal category. Okay, so that's the folding. Now the discarding. Well, for each object A, we assign it a set of discarding effects. So not just one effect like in the original CPM construction, but a whole family of them. And we want these effects to obey a series of sort of sensible conditions. Firstly, they should be monoidally closed. So if I have an effect on object A and an effect on an object B, then their tensor product should be an allowed effect on A tensor B up to some isomorphism. And all this isomorphism does is just rearrange sort of the tensor factors in A and B. Don't worry about this isomorphism for now. Secondly, we asked that the only effect on the unit object is the identity map. And then finally, we want our effects to be essentially invariant under the action of G. So by this, I just mean if we take our effect and we hit it with phi at G, then we should get back our original effect. Again, up to some isomorphism, which just rearranges the tensor factors in A. For more information on these two isomorphisms, you can see our paper. Okay, so given the folding and some chosen environment structure, we can define a new category, CPM, which relies on both the folding and the environment structure. And this is the smallest subcategory of C, which contains both the folded category and all the effects of the environment structure, up to some technical constraints about their tensor product with the identity maps. Don't worry about this. The best way of thinking of this is it is the smallest category containing both the folded category and the effects from the environment structure. Now, like the folded category, CPM category is essentially invariant under the action of G. So once again, these autofunctors restrict to functors on the CPM category. And here they're naturally isomorphic to the identity. And this basically happens because the folded category is essentially invariant under these functors. And we picked effects that by definition were also. Now, the CPM category has a couple of other important properties. Firstly, it's straightforwardly a symmetric monoidal category. Secondly, it's if our original category is dagger compact, one part of our action, an element of our action is the conjugation functor, then the CPM category is also a dagger compact category. Okay. So what's the connection between these CPM categories and field theory, and in particular Galois theory? Well, if we suppose that we have a Galois extension, big K, of some field little k, then there is a map known as the field norm N, which sends elements in big K back down to little k. And it's given by this following expression. So on some element A of big K, it's given by a product over the image of A under each automorphism in the Galois group. Now, this expression looks quite similar to the folding functor that we defined earlier, and indeed it is. So for instance, on the scalars of our category, so on a scalar A of our category, the folding functor acts as to send it to the product over the image of A under each one of these auto functors. Now, if we make an additional assumption that the that the scalars of C form a field big K, then these phi of G restrict to field automorphisms, and they fix some subfield little k of big K. Now, big K is a Galois extension of this fixed subfield, and it can be shown that the folding then acts as some power of the field norm. Okay, so let's go a little bit further with this and sort of perhaps start from slightly the other direction. So let's say that we start with a Galois extension. So we start with big K, which is a Galois extension of little k with Galois group lambda. Then if we look at the category of matrices with entries from big K, the Galois group acts on this category canonically, just as the identity on objects, and then on morphisms, it just acts entry-wise on the matrices. And with this action, we can define a folding functor in the way that we described earlier. Now, the discarding, our aim is to pick discarding maps that factorize via subgroups of the Galois group. So for the whole Galois group lambda, we can define this discarding map, which just joins up all the sort of elements of the Galois group. And then for the normal subgroups of the Galois group, we define these other maps, these other discarding maps. And what these essentially do is they join up all the elements of the subgroup lambda, and then they fold this by the quotient group. So in other words, this whole map joins up the cosets of lambda in gamma. If we take these discarding maps and we close them under the monoidal product, then this collection forms an environment structure. Now, I've restricted the discussion in this talk just to the normal subgroups, since they can be described by foldings that are given by these quotient groups. It is in fact possible to discuss the non-normal ones, but it requires a bunch more machinery, which we develop in the paper, for which there is not time to discuss here. But if you're interested, it is in there. Now, with these discarding maps, we can define decoherence maps, sort of that decohere via each subgroup of the Galois group. And in the idea of these maps is that they when they act on a state, say, they pick out the parts which are fixed by this subgroup of the Galois group. And in doing so, they pick out the parts of states, say, that belong to some subfield of the extension. So this could be seen by looking at a decohered state, say by this map here, and then looking at the symmetries of it. And all the entries have to be fixed by lambda. And in that sense, they have to live in the fixed field by lambda, and thus the subfield of the extension. Now, there are a couple of important properties of these maps. Firstly, they're idempotent, and secondly, they're causal under the associated lambda discarding map. Okay, so the outcome of this discussion is the following. We can define the following categories: CPM, which relies on this Galois extension, and it's just the CPM category where the folding is given by the Galois group, and the environment structure is given by this discarding via subgroups of the Galois group. And these categories have some nice properties. So firstly, they are enriched in commutative monoids, and they're dagger compact categories. The dagger, for any category K-mat, it has a kind of boring dagger just given by the transpose. But if the Galois group contains an automorphism of order 2, then we can define a more interesting dagger on this category, which behaves a lot more like the normal one for quantum theory. The scalars of these categories form a sub-semi-ring S of K. It's quite complicated to write down precisely what big S is, but it's essentially given by the additive closure of these field norms from all the sort of intermediate fields of the extension. The point is, though, that we can think of S, this semi-ring, as the semi-ring of probabilities of our theory. And then finally, these Galois CPM categories have decoherence maps to intermediate CPM constructions, precisely the decoherence maps we defined earlier. And these decoherence maps allow us to move down to intermediate CPM constructions over all of the intermediate fields of the Galois extension. And in particular, it has the full decoherence due to the whole Galois group gives an equivalence of categories to SMAT itself. So that makes these theories probabilistic theories. Okay, so let's finish up with some examples. Firstly, how do we recover usual quantum theory in the language described here? Well, if we start with the Galois extension of the complex numbers of the reals, this has Galois group generated by complex conjugation, which is isomorphic to C2. Then this Galois CPM category is just the usual CPM construction. There is only one interesting subgroup of gamma, and that's the Galois group itself, and that induces the normal non-trivial decoherence map, which is just given by joining up the elements of the Galois group, so the identity and complex conjugation, and just joining these up. Finally, the semi-ring of scalars is just given by the image of the field norm. In this case, that's Z star times Z, and these are just positive real numbers, so we get the semi-ring of scalars is as we expect, R plus. Okay, so now for a more exotic example, take the fifth cyclotomic field. So this is a Galois extension of the rationals with Galois group isomorphic to C4. It has one non-trivial subgroup, which is isomorphic to C2. The states of this theory, so here we have sort of the four elements of the Galois group that we've tensored over. And then we have these two different discarding maps, the one that joins up all the elements of the Galois group, or all four of them. And then this other one that joins up the elements of the cosets of lambda in gamma. So the identity in sigma squared and sigma in sigma cubed. There are two interesting decoherences in this theory given by the two different subgroups. The one of them by joining up all the elements of the entire Galois group, and the other by joining up the cosets of lambda in gamma. And these decoherences give equivalences of categories to intermediate CPM constructions. So formally, we can state this in the following way. If we take the Caribe envelope of this CPM category, then the full subcategory spanned by the decoherence maps can be characterized as follows. So the full decoherence map gives us an equivalence of categories to the positive rational valued and matrices. So this can be thought of as our classical subtheory. And then the partial decoherences given an equivalence of categories to this intermediate CPM construction. And this intermediate CPM construction has a folding, which is given by the Galois group of this extension, which is C2. And it has entries that are the totally positive elements of this field. So these are the ones that are positive under all real embeddings of this field. So putting this together, we get this tower of theories, kind of in correspondence with this tower of fields. And as we decohere through this tower, both the degree of freedom of our systems is decreased, as we can see by the folding decreasing from C4 to C2 and then to a trivial folding, but also the fields over which we are working decrease as we go down from the fifth cyclotomic field to the totally positive elements of this field, all the way down to the positive rational numbers. Okay, so one final example. If we take the seventh cyclotomic field, this is a Galois extension of the rationals. It has Galois group isomorphic to C6. There are two interesting subgroups of this, lambda 1, which is isomorphic to C2, and lambda 2, which is isomorphic to C3. The states of this theory look like this. So again, we've got all 6 elements of the Galois group, and then we have the 2 different discarding maps, one via the sort of cosets of lambda 1 in gamma, and the other via the cosets of lambda 2 in gamma. And then there is another discarding map, which is via the entire Galois group, but that's just given by a composition of these two. So I haven't drawn that here. There are then 3 different interesting decoherence maps, one via the group lambda 1, another via the subgroup lambda 2, and then one for the whole Galois group. And the point is that these maps decrease the degrees of freedom of systems by sort of reducing the folding, but they also reduce the field over which we are working. So here, from the 7th cyclotomic field to this intermediate field, from the 7th cyclotomic field to this different intermediate field, and then from the 7th cyclotomic field all the way down to the rationals. So in terms of sort of these sorts of diagrams, we have this diamond of fields. So we have the 7th cyclotomic field, and then its 2 intermediate fields as a Galois extension of Q in bijection with the Galois group and the subgroups of the Galois group. And then this tower of quantum-like theories. So at the top, we have this, the CPM category given by the whole 7th cyclotomic field. And then we can decohere via these 2 different intermediate fields, which is why this is quite unlike quantum theory. And then there are 2 different ways that we can go via these 2 different intermediate theories that live over different fields and that have different foldings, and then all the way down to this classical like theory at the bottom. Okay, well, thank you for listening, and we'll be available in the chat for any questions you may have.